Okay, so thank you everybody for joining. And this time we have Dongsheng Ge, who is going to tell us about CV or CA. So Dongsheng, please take it away.
Okay, thanks for the introduction, and I'm very glad to share these topics with you. So it's called CV or CA based on two conjectures, and it's a work with Shira Chapman and Giuseppe Podcastro with the following archive number. The question we are asking for this talk, for this paper, is that there are two holographic conjectures of complexity proposed by Susskind. One is the complexity equals to volume conjecture, and the other is the action conjecture. To remind you that these two conjectures are shown in the following graph, the Penrose diagram. The left one is the volume conjecture, where the complexity is given by the maximum volume of a given time slice, and the complexity equals to the volume of this slice over some G Newton and a scale constant. And the other conjecture is evaluated inside a Bach wedge, which is called Wheeler-DeWitt wedge, and it's basically sending light rays towards the Bach. Although various tests has been made on these two conjectures, we are wondering whether these two conjectures are really universally equivalent to each other or not. So that's why I'm putting the question mark here. And in order to answer this question, as a theorist, we used some simple case to analyze these two conjectures, and it's drawn in the cylinder below, where one can embed an ADS2 slice in the middle of an ADS3 slice. And these two ADS2 slice in the Bach act as a defect, and it has the brane action lambda integrated over the metric, the volume. This action so the first term is the usual Einstein-Hilbert action. And for this action, it has been considered by a lot of people. It's the non-domain wall solution, and the resulting metric has the following form, which is parameterized by YRT coordinates. As you can notice here, that this Y is in absolute value. That means we can, for a given time slice, if we take one given time slice of the cylinder, we can have it, put it into two patches, which is drawn on the right-hand side. And one thing to mention here is that all the green lines drawn here are constant Y coordinates, constant Y surfaces, and the red curves here are actually constant R coordinates. And the defect dependence, or the brane dependence, is encoded inside this Y star, which has a relation with the tension parameter given on the bottom. Its tangent Y star equals to 4 pi G Newton L times lambda. Okay, so now we have our tools to analyze the two conjectures. What are we going to do next? We will apply the two conjectures, apply this current case to consider the two conjectures. But as we know that the ADS space-time is an infinite space-time.
Sorry, can you hear us?
Yes.
Can we go back to the previous transparency? Sorry. Yeah, super. So let's see. So in this metric, which is the radial? So R is the radial direction ADS. Yes.
Actually,
No.
R is the direction of ADS2, the radial direction. And the radial direction of ADS3 is not very explicit here because both Y and R had some components in the radial direction. For example, if we follow, okay, let's put it like this. This antipodal points here, it has the coordinates y equals to infinity, and r equals to infinity, and y equals to 0.
Okay.
And if you follow the green curve and take it far more to the border, to the boundary, this black curve on the leftmost side will be y equals to infinity. So it's the ADS boundary. That means either y or r goes to infinity, we approaches the boundary of ADS3. And the metric written in this way is like a robbed geometry. This cosh is the robbed pin factor, and things inside the square, this dt dr thing, is the metric for the ADS2.
Okay.
Shall I move on?
Yeah. Yes, please. Yeah. Thanks.
Okay. Yeah. So for the ADS spacetime, it's infinite. It has infinite volume. We will put a cutoff to get it, to regulate it. The tricky thing here is that in the defect zone, the Pfefferman-Gram procedure doesn't really apply here, since you can see that one point will be extended to some finite length curve, and this doesn't have a uniquely defined Pfefferman-Gram coordinate here. And in order to cure this this cutoff choice, we choose it in the following way. So in the pure ADS part, we use the usual Pfefferman-Gram cutoff, which has a constant distance to the boundary. And in the defect zone, instead, we choose a constant R cutoff. Remember the constant R curve before. It has another nice property, which is that constant R curves are also spatial geodesics in a given time slice. And the benefits for this cutoff choice is that first, we are following a geodesic, a spatial geodesic in the defect zone. And secondly, it is smoothly connected to the ADS, to the cutoff in the upper half disk. And a third benefit we can gain from this choice is that when we glue these two pieces together to make it one, we don't have to consider an extra joint in the CV conjecture, in the CA conjecture. That means the two surfaces, when glued to each other, it will be smoothly connected. And yes, with this cutoff in mind, we first do some calculation in the by considering the CV conjecture. I took one of the bubble in, so it has two pieces, one left, one right, or one up, one down. I just took one of these to illustrate the CV result. So it can be divided into two parts, V1 and the V2. V2 is the usual pure ADS 3 part, and the V1 is related to the existence of the defect. In the V2 part.
So you're saying that this darker yellow region is like ADS result because you have like a cosh, and this cosh has like an exponential, dominant exponential behavior, and this gives you like something that to an excellent accuracy looks like ADS. Is it the reason, or there's something else?
I think it's because here we didn't do, it's really a pure ADS case if we don't see the defect. It's the usual ADS procedure with...
I know the usual ADS procedure, but you're saying that the geometry above this line that you draw is precisely empty ADS geometry, is what you're saying?
Yes, exactly. It's purely empty ADS3.
Okay.
Actually, this extra piece is also somehow you can regard it as an extended piece from the pure ADS geometry.
Okay.
Yeah. And then for the V2 part, we adopted another global coordinates, which is the theta phi coordinates. Phi is now the radial direction of ADS. And theta is the angular direction. And as expected, it has 1 over delta divergence in the ADS, pure ADS3 for the CV result. And the V1, instead, we choose the YR coordinate, which has been shown before with the red lines and the green lines. Since the cutoff, as I have said, it's a constant R cutoff, it's a constant R curve. So that means we can evaluate this thing with 2 definite integrals, which is easier to calculate. And it turns out to be, it is a log divergence with dependence on the defect parameter, sim_y star. And then we add up these 2 pieces together and divide it over G Newton and the length scale, the ADS length scale. We arrive at the result in the bottom. There are 3 pieces. The first piece, and this CT here is the Brane-Hainaut procedure relating the central charge to the G Newton. The first piece tells us it's the leading divergence is 1 over delta, and we took a factor of 2 outside, so actually it should be the length of the boundary, which is 2 pi. And the second term is a result of the defect, and it is a log divergence. It's a new log divergence appeared here. It depends on the defect. The third piece is kind of interesting. It's a topological piece which has been analyzed by Echtermanger and the collaborators in this paper. So in an ADS3 case, it has a simpler form, which is shown here, the leading divergence over delta, and then the pi q. Q is the number of entangling intervals. In our case, it's 0 because it's the whole CV. And the chi is the Euler characteristic for the entangling region. And here it is 1, so the topological term is -2 pi, and is consistent with the result we have here. After seeing the result of CV, we can move to the CA part. So for the CA part, the tricky thing here is that how we can consider the Wheeler-DeWitt patch. In a given time slice, we know that it, for example, on the left-hand side, we know that it is a pure half ADS plus some extra pieces, which represents the defect. And now we want to get the Wheeler-DeWitt patch, which means basically we just need to get the boundary of this Wheeler-DeWitt patch. And we send the light rays from the ADS boundary to the bug into the center. The blue surface is for the pure ADS3, which is a half cone. So it can be viewed as a light cone, the past light cone generated from the top points, from the summit. And then there should be some other pieces that cover cover the defect region. And it turns out to be that it's the light cone generated by those two antipodal points. And the light cone, the green surface is a part of the light cone of these two antipodal points. So in the end, when they meet each other in the center, they will form some kind of tent-like structure for those two light cones. And in order to consider the whole CA, we have also another copy of the two objects here. That's the past pieces of the geometry. And let's now look at only a quarter of it to see what's going on there. And as I said before, the blue surface will be the half cone, which is a pure ADS3, and the green pieces, which is denoted as S2, will be the light cone generated from the antipodal points. So the boundary of this Willard-Witt patch will consist of two light cones. One is somehow S2 and the other is S3. And the red surfaces drawn here is the cutoff surface extended in the time direction. And the orange one is in the ADS3 part, and the red one is in the defect zone. And what are the actions we are going to evaluate for this conjecture? It consists of the usual Einstein-Hilbert action, which is the first piece, and then it will have some time-like surfaces, which will be represented by this extrinsic curvature or the Gibbons-Hawking term. And we also have the null surfaces, which are the light cones. In order to, as it's known that the null surface, the metrics on the null surface are degenerate. And the prescription for that part is known as that we can still get the null normal vector, but we will represent in a way with kappa. Kappa is characterize the parameter we choose here, how far it is deviated from the geodesic parameter. And the second term has been analyzed in the paper by Myers. It's regarded as a counter term. This term is added in order to keep the whole action to be parametrization invariant. And when the surfaces meet each other, it will generate the joint term, which is shown here in A, and it's a codimensional 2 term. The last term is intrinsic to the current case we are considering, which is the contribution from the defect. And then we need to analyze the contributions separately. First from the bulk, and then to the surfaces and the joints. Since our main focus here is the defect zone, I will only talk about the contributions from the defect zone here, while the other, the whole calculation is presented in our paper. In the first picture shows the bulk division. No, here it shows the bulk division. It is a projected picture. We didn't draw 3D here. So B2 is the projected picture of the half cone to a given time slice. And the B1 is the opening of the tent on a given time slice. And the red curves red dotted curve are the cutoffs. And B1 contributes to the defect region. So we list here its contribution. It's also a definite integral except the part with dt, since it has there are some dependence of r and t in the future cone. And that's the result. We see that here. It depends on the defect. If y star becomes 0, then this contribution goes away. The same analysis goes for the surfaces and the joints. In the surfaces, in the defect region, we have two null surfaces, S2 and S4, which is the cutoff surface, the constant cutoff surface. Here, I would like to show you the calculation of this S2 so that you get more convinced. And we need to adopt a parameterization for this surface, which is denoted as lambda. And the good way of parameterizing this problem we found here is to parameterize in the following way. And with these choices of the internal parameter lambda, we can define the null normal vector in the following way, which is the x mu. X mu is the coordinates, and the lambda is the internal coordinates. And we get the null normal vector. One can see that its norm will be 0. And to remind you how we obtained kappa is shown in the geodesic equation of k, and then is proportional to kappa. And the surface properties, since it's a null surface, we obtained the metric. It's a constant, L squared. And the expansion of the null rays is 0. And then the kappa is calculated to be like this with a normalization factor N2. And the result is obtained by integrated over the metric, and it is a log divergence dependent on the tension, on the brane tension. And then we can obtain the all surfaces contribution and the joint contributions by adding them together, which is shown here. We have 2 S2 and 2 S4 and 2 J2. J2 is the joints intersected by the cutoff surface and the null cone generated from the antipodal points. And also 1 J3, because when they meet together, they will have another joint. And then there will be a factor of 4, since we mentioned we have a left and right and a future past. And the result is given here. It's a log divergence -1, dependent on the defect, on the defect. And the final piece is the defect contribution. Since we know when we glue these two patches together, we will have it will be characterized by the Israel junction, which relates the extrinsic curvature of that gluing surfaces, left one and the right one. The square means right minus left. And that's the trace of the extrinsic curvature. And equivalently, it is to say that we add 2 extra Gibbons-Hawking term on the gluing part. This is the effect of the Einstein-Hilbert action. And the resulting behavior of the defect contribution is that we add the contribution from the Einstein-Hilbert action and the brane action. It turns out to be that it's minus of the brane action, and then one can calculate this brane action in this surface SD, and turns out to be the sinh 2y star over 2 pi gn times a log divergence. And if we sum up the three terms, we see that this sinh y star will cancel with a term in B1. Sorry to go back, but this sinh 2y star will cancel with the defect divergence, and this y star of B1 will cancel with this surface joint term. Thus, in the end, we will obtain 0. That's really non-trivial. It shows that we didn't see, or the CA cannot really see the existence of the defect. Thus here, it shows that CV and CA behaves quite differently in terms in the presence of a defect. And to make a further analysis, we considered the case of the subregional conjecture, which has been proposed by Myers and collaborators. There are also two, one is CV and one is CA. It is related to in the field theory side is the reduced density matrix, and in the box side, so for the CV, it will be bounded by the RT surface, and on the other side, it will still be bounded by the ADS bound.
Sorry, I still have a question about the previous transparency. So
yes,
when you started considering defect, like were you expecting, based on some earlier works or something like this, such a cancellation, or this came as a complete surprise?
What do you mean?
Well, I'm like, you had some reason to consider defects and CA and CV for defects, right? So,
right.
So the fact that you did defects like were led because you were expecting some sort of a cancellation to occur, or like that's something that came up as a surprise.
I don't think we expected it to cancel, but it turns out that in the CA part it canceled.
Okay.
At the beginning, you mean for a general consideration of purely the geometric consideration with the extrinsic curvature, right?
So do you think this is like an artifact of ADS3, or like if you go to higher number of, like you can first of all consider also defects in higher number of dimensions, right? And, like we have some expectations.
Sorry, I cannot hear you very well. Can you say it again?
Oh, like what I was asking is like if you can presumably consider defects in higher number of dimensions, right?
Right.
So do you have an expectation like that such a cancellation would happen, or it's some sort of feature of you know of ADS3 basically, or ADS3 physics?
Yes, that's a very interesting question, because so far we only constrained ourselves in ADS3.
Yeah.
In higher D dimension, it's not sure yet, because you see why it cancels. It's really because that when we have this IB, this defect contribution, when we sum the defect action and the contribution from the Einstein-Hilbert action, it is the minus of the I lambda. But maybe in higher dimension, that there could be another factor that cannot, some extra factor in front of this minus I lambda that cannot really cancel with, for example, the Bach contribution and the surface joint part. And this is not sure yet. But we think we are interested to working on that. And yeah, we have considered a bit, but no result yet.
And like another stupid question. So if you consider evaluating the partition function in ADS defect and without the defect, do you get the same answer, or there's a difference? I'm not talking here about like CA, but like if you just calculate the Euclidean action in the full spacetime, do you get the same answer in the presence and absence of the defect, or not?
I don't know. Okay. I don't know about I don't know about that. I think, no, I don't know. Sorry, I don't know.
But for this cancellation to occur, like what was really important is that we had like these additional terms, you know, like this joint terms, the surface terms, and like the whole contribution added, like just gave you the answer that is the ADS3 answer.
Yeah, and it's really due to I don't know how to say, but for example, I think it's really non-trivial because you see that when we consider all the pieces inside the defect, it cancelled. But if we consider all the pieces in the ADS3, we get some contribution. I don't know. I don't know how to consider about this problem in a higher level.
Okay. Oh, thanks. I mean, like, let's move on.
Okay. Yes. So yes. Okay. For the subregional part, first we have to get the RT surface for the in presence of the defect, and basically is that we have we started case with one boundary point in one patch and the other point on the other patch, and then we shoot the geodesic towards the bulk. Ideally, they should meet each other on the gluing part, and it turns out to be a minimizing condition. And the minimizing condition will, and then we minimize the addition of the two geodesic. The minimizing condition, it turns out to be that it will be the average of R left and R right, which are the coordinates of the hooking point on both sides. We obtain the general expression of this geodesic so that we can calculate the boundary entropy that has been proposed by Karsh, a holographic way of calculating the boundary entropy by Karsh and Takeyanagi and the collaborators in this paper, where they have calculated only in the symmetric case where R left equals to R right. And the result is proportional to Y star. And we see here, the result we obtained here is cosh Y star plus sinh Y star, and then the sinh Y star is over a cosh of R left minus R right. If R left and R right are equal to each other, then we came back to the case they have considered. So it's a kind of generalization, but it's a trivial one. And then the region to be considered is within the RT surface and the boundary. And with some calculations, we can show that it has the same structure as before. It consists of three parts. The first part is proportional to the boundary length. The second part is a result of the presence of the defect, and the third term is a topological defect. It's a topological term, and we see, because here the Q characterizes the interval will be 1 here, so now the topological term will be only half of that of the whole CA part. And with the same spirit, we consider the sub-regional CA conjecture. And here we only consider the symmetric case. In order to consider the sub-regional CA conjecture, we need to find the entanglement wedge, because we know that the sub-region is bounded, is a common region of the Wheeler-DeWitt wedge and the entanglement wedge. And the entanglement wedge in this symmetric case have a very nice feature. Well, it's basically we have to send light rays from the RT surface towards the boundary. And in this case, it can be viewed as a future point of the antipodal points. Sorry for the noise.
Yes.
It is a point in the future. It can be regarded as the antipodal point from the future, and is sending light rays to the past. This means we will have the boundary of the entanglement wedge in one of the patch to be tangent HR equals to cosine theta r minus the time. One can see that if we use a constant time slice to intersect the boundary of entanglement wedge, then we will get at each time slice, it is a constant r. It means at each time slice, it gives rise to a spatial geodesic. And with this extra intersection from the Wheeler-DeWitt wedge and the entanglement wedge, what we will have now to consider is the common subregion of these two wedges. I will only show the result here. So again, our main consideration here is things inside the defect zone. So I will only give the result in that zone. So it is the zone that is inside this red curve. And yes, the thing that one has to notice here, this dotted line inside this defect zone, this dotted blue line, it is the intersection. So it's the projected one of the joint, which is intersected by the boundary of the Wheeler-DeWitt wedge and the entanglement wedge. The nice feature of this curve is that it will be a constant R curve on a given time slice. So that it would be very nice to walk in the YR coordinates here. That's the nice feature of the blue dotted line here in the defect zone. Yes, and then for the Buck contribution is the Einstein-Hilbert contribution, which contains of B1 and the B3, and the result shows that it's totally dependent on the defect, and then with some divergence term and some constant term. And for the joint and the surface term, we have S2, S8, and S4. S2 is the boundary of the Wheeler-DeWitt wedge, a part of it, and S8 is the boundary of Wheeler-DeWitt of the entanglement wedge, also a part of it, and S4 is the cutoff surface, the constant R cutoff surface. And there is an extra J6 joint which is formed by the it is formed by the entanglement wedge, the one in the future and the one in the past. They will form a joint J6. So adding those surface and joint contributions, we will obtain also a total factor dependent on the defect, and then a log divergence plus some constant term. And as before, there will also be the defect contribution, which in this case is minus the action of the brane action. And as expected, it's also dependent on the defect. If we add these three contributions together, one see again that they will go to 0. Which means that in the sub-regional case, it also shows a totally different feature for CA and CV in presence of the defect. And we would like to know how, like, since now we see these two conjectures are different, so we are thinking maybe one should be will be more favored than the other. So how can one see it? We considered some simple boundary model, which consists of two conformal defects on the antipodal points of a circle. It is a model that has been considered by Bacchus and Augury, De Boer, and the collaborator in this paper. And the defect contribution will be written in terms of the matching condition of the two compact bosons on the left side and on the right side, which are marked by phi plus and phi minus. It is a matrix relating the derivative of the fields of the boson in this way. So there should be two such matrix equations, one for each defect. And followed from the proposal or the consideration by Jefferson and Myers, where they considered the Gaussian states of in terms of the Nielsen method, and they relate the complexity to the frequencies or to the spectrum of the harmonic oscillators. And in that spirit, we obtained the spectrum by imposing such matching conditions on the defect. And the thing we obtained, or the spectrum we obtained here, since it's a massless case, so the spectrum is the absolute value of the wave vector. And that's the result of the spectrum. So there is a defect dependence piece, because we choose one to be lambda and the other to be lambda prime for a general analysis. But for it to be compact, actually this lambda has to be 1 over lambda prime. That means in the case, actually delta should vanish, meaning that in the simplest boundary field theory we considered, that the spectrum won't see the change of won't see the presence of the defect. An intuitive way to understand this phenomenon is that, for example, we have a traveling wave that moves clockwise. When it passes through the first defect, if it will get some enhancement, and then when it passes through the second defect, it will get weakened by the second defect. And in this case, these two effects will cancel. One, the enhancement and the weakening will cancel, so that intuitively the spectrum won't change by the presence of the two defects of the same type. And the formula they obtained in their paper by Jefferson and Myers is that the complexity will be the summation of the log of the frequency or the spectrum over a given spectrum, over a given frequency. And in the case, we can choose this kappa, which is the cost, to be 1, and that's the result we obtained. In the second line is the result, because we have also choose n to be a cutoff dependence, and it has some expression with lambda. Lambda here is the UV cutoff. So the leading term is lambda log lambda for the divergence. And then it has a log divergence piece, which doesn't depend on the defect. And the third piece, we know that for compact boson, it will goes away. Thus, we conclude, while comparing the field theory consideration with the bug consideration that seems from the field theory side, we also cannot see the defect contribution if we are in the model with compact boson. And but it can never match the result of the CV part because in the case of field theory, we have a log divergence, but the log divergence is not dependent on the defect. While for the CV result, it has a log divergence and it is dependent on the defect. So it cannot really match CV. And and also it cannot really match CA completely because it has a log divergence. So it seems to us that it might favor CA rather than CV, but we cannot say this very concretely yet, as there are still some things to explore with the setup. So one thing is that if we go to higher dimensions, as Michael has proposed, there might be some difference, or the CA can again see the existence of the defect. And also it would be quite interesting if we consider not just the codimensional one defect, but like some higher than codimensional defect. And then there is another complexity proposal by Takiyanagi, which is the Liouville complexity with the tensor network intuition. So maybe in this case, one can also consider the Liouville theory with a defect. And yeah, this might be interesting to see how this Liouville complexity could cooperate with the existence of the defect. And as we have said, in the field theory case, we adopted the field theory construction that only considered the Gaussian case. And a recent work by Myers and the collaborators, they considered the coherent states holographically, where they introduce a scalar field in the box. And seems like in that way, the holographic theory is more complete. And one more thing is that the field theory side, since the zero mode in the massless case will lead to IR divergence. And so far, it doesn't, I don't know if anyone who has worked out or has thought about the complexity related to the zero modes, which characterize the degeneracy of the state. It might be interesting to consider. And that's all. Thanks a lot.
Thanks, Dongsheng. Are there any more questions or questions from people online?
Well, I had like I'm just wondering if I understood it right. So I just want to get like a clear statement. So when you calculate the action results, when you said that the defect doesn't contribute, you were saying that you calculate the action in the presence of defect. From this, you subtract the result in the absence of defect, and you get the same result. I mean, you get zero basically.
Right.
Okay, so this is the situation.
Right. If you
saying that in field theory, in the case that you addressed, this wasn't happening, right?
Right. The defect won't appear.
The defect interfere, but like what we saw in other field theory considerations is that the answer that you get from field theory depends on various factors. So there's like this question of a choice of norm,
Right, right.
It's like the L1 norm. Then for L1 norm, there's like an issue of the choice of a basis. So like depending on what basis you pick, you get different answers. So like when you say that in field theory the defect interfered, did you try to like various options to explore to see if it's always the case?
Right, exactly. So here we only pick the KX1 case, which I think is equal to the L1 case. And we also choose this K to be 2 to try a different choice. But no, it doesn't really, we cannot get a defect-dependent log divergence in any case.
Okay.
And that's, I think, this log divergence is quite important if one wants to be in favor of the CV conjecture, since it's always a log divergence with defect dependence parameter in front.
I see.
And indeed, since this consideration, it only considered the Gaussian states. So it's a group manifold that consists of all the gates that transform from one Gaussian state to another. But recently, the idea I have is that I don't know whether it's a good idea to consider Gaussian states as the holographic duo or not, because you know that the new paper written by Rob, they consider the coherent case, and it seems that makes the holographic story in a very concrete manner, or in a much nicer manner.
Well, I agree. Yeah, I mean, like, I believe that like something in between might allow us to address like some of these. I mean, like, at least partly the question of holographic complexity proposals, like trying to combine like the coherent states approach with deep counting. Actually, like this also like rings a little bit. I mean, it has a little bit of a flavor of pattern optimization. So
Mm-hmm.
as a community, we're somehow getting there.
Right.
Right. Well, anyway, thanks.
Okay.
Thanks a lot, Dongsheng.
Thanks for listening.
Thanks. So thank you everybody for joining. See you. We're gonna